All right, hello everyone, this is Mr. MathWell here, and we are in Environmental Science 20 class, and this is the beginning of Unit 2, so this is Chapter 3 today. We're going to take a look at it in your textbook, and this is video 1 of 2, and you shall see this video up on MrMathWell.com right here. Environmental Science 20, Chapter 3, lesson video 1 of 2. That's going to be up on MrMathWell.com. So, as we head back to the notes here, you should have in front of you a set of blank notes, and I will show you the highlighted, underlined words that you can put in your student version of the notes. That also should be up here, right here, Chapter 3, student blank notes that you can print out if you don't have those in front of you. So, essential science background, starting on page 54 of your text. Table 1 shows forms of energy. There are two main categories of forms of energy. One is kinetic, that is the energy involved in motion, and the second is potential energy, the energy related to position. So as this girl is standing up here on this platform, she holds the ball. This ball possesses potential energy because gravity will act on it and will move it if she lets go. So there is potential for work to be done, potential for some impact to be made. That's potential energy of position relative to something else. And then as she lets it go, that potential energy then begins to be converted into kinetic energy as the ball begins to accelerate towards the floor. Yay. Here are some forms of energy that you should recognize. Solar. Solar is from the word sun, sol, sun. It is energy or radiant energy from electromagnetic waves traveling through space from the sun. So you see solar panels, right? Okay, so solar energy is from the sun. Sound energy is the energy related to vibrations of atoms. So when you have a speaker like this, very big loud one, the cone moves in and out, if you notice, and it pushes the air molecules, and those air molecules are pushed through space. They collide with one another, and they go into your ear and collide with your eardrum, and that sound that you hear, that your brain interprets, those little vibrations in your ear, interprets that as sound, but that is literally energy of vibration of atoms in the air between you and the sound source. Thermal energy is the energy that is heat energy, or the energy of random motion of atoms and particles. So if particles are very hot, they have a high degree of random motion, and that will spill over into other particles. So if you have like a really hot particle like this and it bumps into this one, then they both kind of become energetic, and that's how heat is passed. Okay, so when you feel a wave of heat, that's high energy particles intercepting your sensory particles and the skin, and your particles start to vibrate a little bit more, and you feel that as heat energy. Okay, moving on. Chemical energy, energy that is contained within the bonds of atoms, and that says bones. That is incorrect, Amundo. We shall fix that right now. Not the bones, the bonds. Oops. So the E has to change. Sorry, bonds. Like that. Like that. Still looks weird. Okay, bonds. So you realize that if you have like a water molecule or something, so you have a big oxygen molecule here, and that's attached to a hydrogen atom here. Sorry, oxygen atom attached to a hydrogen atom. You have a water molecule. Okay, water is H2O. Wonder why that is. 2 H atoms and 1 oxygen atom, H2O. And so when you add energy, you need energy to break this bond. So there's energy that's contained within the bonds between atoms, and so you would need to add a certain amount of energy to break this bond. Wow, that just disappeared on cue. To break the bond between the hydrogen and the oxygen. You can split them up, hydrogen-oxygen atoms, electrolysis, and if you force them back together, then you get the energy to come back out. So energy goes in to break bonds, energy comes out when bonds are broken. My computer is not happy. I don't know why. Anyways, okay. Hello. Let's get back to the notes here. Oh, we're sorry for crashing. This is not good. Okay. I love technology. Pause. All right, here we go. See if we can get back to it here. So yeah, there's energy contained within the bonds of atoms. Okay, so it takes energy to break those bonds, and you get energy back if bonds are made. So that's cool. All right, elastic energy. It's the energy stored within a stretched or compressed object, such as an elastic band or a car bumper. So elastic band is the easy one. If you stretch it, there's energy there, right? If you let it go, something's going to happen, right? A car bumper. Okay, think of that as something that's compressed, and it's able to absorb an impact, because it will kind of like it will absorb that impact, or it could, like, push against the impact, right? So if something is compressed, that will pop out. If something is stretched, it will pop back in. So that's the same kind of energy. It's elastic energy. Gravitational energy is the energy due to position of an object affected by gravity. So we talked about potential energy because of position. Gravitational energy would be the specific energy that will act upon an object due to gravity. Nuclear energy is the energy stored within the nucleus of an atom. So if you were to actually crack a nucleus apart, that would be a nuclear fission reaction. You would release an immense amount of energy, and that's atomic bombs, nuclear bombs. That's what happens there. Electrical energy is the energy stored in the separation of positive and negative charges. So if, because positive and negative charges attract, if you separate those, you have this energy, right? You have this force. That's electrical energy. And electrical potential energy is what kind of forces electrons to move through circuits to lend that energy to light bulbs and different things that use electricity. Awesome. All right, mechanical energy is the energy is the sum of kinetic and potential energy of an entire system. So it's kind of like a whole entire system. Mechanical energy is sometimes used as the energy to do work. Okay, so to move something. Yeah, mechanical is actually physical things interacting. So the sum of all energy in a system would be the ability to do work, is another way to define energy. Okay. Energy can be converted from one form to another using an energy converter. So on page 55 of your text, you can read about energy converters. Talks about how chemical energy is released from a battery, how mechanical energy or energy of motion, kinetic energy, comes from electric cars or from combustible engines. That kind of thing. So one energy form converted to another energy form is what we're really interested in when we're talking about usable energy. All right, so into 3.1 now in chapter 3. An energy resource provides energy to bring about movement or change. A sandwich and gasoline are both energy resources. Gasoline has a higher concentration of energy-rich molecules and so brings about much more movement or change. So you put gasoline into your car, you do not put sandwich meat into your car. Gasoline, again, high concentration of very energetic bonds in the gasoline molecules. And so when that is combusted, boom, you get all this energy that runs your car. If you eat a sandwich, you have enough energy to go about the rest of your day. That's a lower level amount of energy, but again, your body breaks down that sandwich and gets the energy from the bonds and reactions of molecules in the sandwich, that kind of thing. So, energy resource is one that can be used to bring about movement or change, and I think I just missed something. Nope. Okay. A non-renewable energy resource is an energy resource that is not replaceable once consumed. So the term is fairly straightforward. It's non-renewable or not reusable. Okay? Fossil fuels like oil, natural gas, or uranium for nuclear energy are common examples of non-renewable energy resources. So if you use it up once and can't use it again, it's non-renewable. Renewable energy resources are energy resources that are available on a continual basis. Examples would be solar. As long as the sun shines, we have a renewable source of energy. Wind. The wind blows because the earth spins. We have movement of air, and so we will always have wind happening. Now, sometimes a lot of wind, sometimes virtually no wind, right? But we do have that as a renewable resource. Hydro. So the movement of water, whether it's falling water or it's the movement of tides coming in and out, which we'll talk about later. Hydro, we kind of have water on the world, on the earth, and we can use water and gravity and different things, the interaction between the sun and the moon, high tide, low tides, that movement of water is hydro energy. Geothermal, geo means earth, thermal is heat, so the heat from under the earth can be used as a renewable resource, because the heat inside the earth from the center of the earth is not going to go cold anytime soon, so we can continually use that as renewable energy. Biomass energy, so biomass, that's like wood and stuff like that. So yes, you can burn wood. We do have a constant supply of wood, even though we have to be responsible with that. But you know, trees grow, throw seeds, trees grow, throw seeds, trees grow. So technically it's renewable, although that bunch of wood or the waste or whatever it is that you're burning, that stuff is not renewable. But as a whole, the biomass is you know, stuff that regrows. Okay, so we can kind of reuse it. And then wave and tidal energy. So yeah, that's the coming in and coming out of waves, or of tides, sorry, like in the ocean. You know, high tide when the water's high, low tide is when the water is way out there, it's really low. It's because of the interaction between the earth and the moon, and basically the water is fluid, and so when there's an attraction between the earth here and the moon up here, let's say, then the water in between kind of gets sucked towards the moon, high tide, and that kind of thing. So when that interaction, then the water kind of sloshes around and becomes high in other places and lower in places. So it's kind of cool. Read about these energy resources, page 58 and 59 of your textbook. Make any special notes in this space below. Look at that, a lot of space for you. Let's keep going. Society's need for energy has increased many times over since the dawn of creation. You can read a brief timeline on page 60 and 61 to kind of see where we've come from day one to today about our energy sources and the need for these energy sources. Section 3.2. Let's study further fossil fuels and other non-renewable energy resources. So coal. Coal is thought to be formed over long periods of time under immense pressure and heat. We find this underground as a result of compressed organic material that has been starved of oxygen, and under these conditions produces a dense carbon-based fuel called coal. So carbon is the main constituent in organic material, and if you compress that and let it rot and starve it of oxygen and lots of pressure and heat, then this carbon-based substance that is very rich in these bonds that have a lot of energy. Remember we talked about that? So you get coal is what it's called, kind of a dark black hard kind of rocky sort of substance that can be burned and releases a large amount of energy because of the bonds in the material, and carbon bonds are pretty strong. It's relatively easy to mine. It's underground. It's relatively easy to get to it and to bring it up. It's easy to move, trucks or trains or boats. And but it's the largest contributor to excess greenhouse gases in the atmosphere, and so its use has been declining. So in the the need for and the desire for renewable energy resources, for polluting less as the population grows and as the earth kind of deteriorates a little bit, as our air and atmosphere start to degrade a bit, we want to try and it'll be a little easier on the earth and produce less waste, and especially less harmful waste. Coal has been reduced a little bit over the years. Some countries and places still use an immense amount of coal for their energy sourcing, but yeah, we're trying to get away from creating so much pollution by burning coal. And back in the day, it was easy to get, and this what was used to even heat houses and stuff like that. Like you just burn coal all night, and that keeps your house warm in the winter and stuff. Oil. Okay, crude oil, also known as petroleum, is created in a similar process as coal. Oil is mainly found underground in deposits of sedimentary rock called reservoirs. Drilling down to these reservoirs and sucking out of the oil is how crude oil is extracted from the earth. Literally, you drill a hole and you just suck all the liquid oil out. So coal is is hard, solid. Oil is very similar to coal, but it's the liquid, right? It's liquid oil. Crude oil is then transformed into all sorts of things like gasoline for our cars, plastics that we use every day, even in our technology, lubricants, and somebody asked me about lubricants too the other day during the lesson last time, and lubricants are basically slick, liquidy gel substances that provide an easier, less friction. They kind of like get in the way of things that are moving over each other, and so lubricants like oil, even oil is a lubricant in your engine, right? If you have a car, you have to fill it with oil. That's because all the metal parts that are rubbing together to make your engine go, they heat up, and the lubricant is basically helps the friction to be reduced and the heat to be reduced. And there's lots of other things that oil is responsible for that people use every day. Oil is transported from one place to another, sometimes using boats, trucks, pipelines, where pressure is applied to the oil in the pipe and the oil is moved over long distance. That's how pipelines work. Oil pipelines are often buried underground, and when that's not possible, such as in rocky or mountainous areas, they are placed above ground. Every effort is made to secure these pipelines, but sometimes oil leaks will occur and interfere with local ecosystems. So yeah, much of the oil is from the well is pumped through a pipeline system, and it's basically sucked from one place to another, or pressure is applied on one end and pushed, that kind of thing. Yeah, natural gas. Okay, what about natural gas? Let's make sure I didn't miss anything. Natural gas is found in thin layers of sediment rock above oil reserves. Gas wells are drilled down into these reserves, and gas migrates up the well. So you have your oil, and then kind of above that is what is the gas that's kind of been released and trapped inside the rock. So if you tap down not quite as far, you kind of get into the gas areas. So fracking, you've probably heard of fracking. It's slang for hydraulic fracturing. And that's a method of creating high pressure fluid pockets in the rock layers to basically create small cracks in the layers or open up the layers so that more gas can be free to travel through and bubble up to the surface where it can be collected. The issue some have with fracturing the rock in this way is that drinking water reservoirs can also be affected by increased gas flow underground. So if you think about a pocket of water here and someone's fracking over here, and this gas is trapped, but all these cracks are made now, well, the gas will migrate up, but it also could migrate over into the well area. And so there's lots of regulations of where you can frack, and you have to stay away from the water reservoirs and so many meters above them or whatever. So they're really careful with trying not to affect the groundwater. But yeah, sometimes it happens, and people are a little freaked out, rightly so. If you live out in the country and you get all your water from an underground well, a reservoir, and someone comes in and they want to frack to kind of get all this gas moving underground, it's like, that's my water down there. I don't really want it full of kind of weird gas. So there's always that little conflict, and everybody tries to, it's regulated, I think, that enough so that there's minimal instances of bad things happening. But okay, so read and discuss the advantages and disadvantages of using fossil fuels as an energy resource. That would be on page 67 of your text. Think about what your position would be. Some people feel strongly against fossil fuels and the use of fossil fuels. Some people are like, we need it to live. I'm okay with it. Record your notes and your thoughts in the in this package. I will be getting you to hand this package in for some free marks. If you've been paying attention, been filling in the notes and writing down your thoughts and answering the questions and things like that, I'd like to see that and give you some homework marks here. So I'll be ready to hand this in. Nuclear energy, this is close to where we'll stop for today in video 1. But nuclear energy inside a nuclear reactor. So uranium-235 atoms are split. Remember we talked about nuclear fission, okay? That's when this is split. The process is called fission, and it releases an enormous amount of thermal energy. On page 7 in your textbook, I will get you to read about the CANDU nuclear reactor pictured below here. It's one of Canada's famous nuclear reactors over the years, and you can read about kind of how that works a little bit. Although nuclear reactors can provide an immense amount of energy with a small amount of material, the radioactive material involved can be quite dangerous. The waste that's generated in a nuclear reactor, called tailings, are called tailings, but can be harmful due to its radioactive nature as well. So, when you get some waste, you get energy, all this energy that you can create and send away, great, but in breaking those particles up, there's still some particles that kind of sneak through that are still bubbling with this harmful radioactivity, and so some of the waste is harmful as well. Being radioactive means that some destructive energy is spontaneously radiated from the nucleus of the atom. So you've heard of radioactivity, you've heard of radioactive before. It is dangerous on a nuclear level, and it can really scramble your atoms, like in your body. It can really cause your atoms in your body to be destroyed or to be harmed, to be mutated. If it gets into genetic areas of your DNA or your makeup, then that can be passed on and everything like that. So yeah, radioactivity, bad. Okay. Uncontrolled radioactivity is bad, I guess. And, if you're doing radiation to help you with a cancerous lump or something, radiation's good, right? If it's controlled, like a laser beam. But if it's like just everywhere, it could really affect things it's not supposed to affect. So on page 71, there are listed again. I'm not going to list them here, but I'll let you read that, please. Advantages and disadvantages of nuclear energy in your textbook. And on page 72 and 73, there are case studies of nuclear accidents and public safety concerns over the last 50 years. And that's where we'll end here today. That would be part 1. So part 2, we'll talk about section 3.3 here in your videos. So, yep.